Imagine a war happening inside you right now.
Right.
And I don't mean that metaphorically. I mean a literal microscopic battlefield where millions of rogue cells are, actively trying to stage a coup.
Mm.
And your body's specialized security forces are quietly, brutally assassinating them before you even know they exist.
It's happening constantly.
Yeah. You wake up, you drink your coffee, you go to work, completely unaware that your immune system just neutralized a threat that honestly could have ended your life.
Exactly.
But here is the terrifying paradox for you to think about. If our internal security is so good at its job, what happens when the enemy learns to, steal a security uniform?
Uh-huh.
What happens when it learns to hijack our own biological communication lines, deploy chemical smoke screens, and build walls made out of our own peacekeeper cells?
Well, it creates an incredibly complex, highly adaptive adversary. I mean, when we talk about cancer, we're not talking about a static disease.
Yeah.
We're talking about an evolutionary arms race playing out in real time within human tissue.
And that evolutionary arms race is exactly what we're wading into today. Welcome to the Deep Dive. We're taking on a topic that is as formidable as it is fascinating, which is tumor immunology.
It's a massive topic.
It is. And the goal for our time today is complete, uncompromising coverage, zero omissions. We are exploring the foundational mechanics of how a cell goes rogue, the highly coordinated way our body fights it, the dark arts cancer uses to evade destruction, the molecular footprints doctors use to track it, and finally, how modern medicine is engineering our own immune system to strike back.
And to guide this exploration, we're relying on a truly exceptional set of source materials. We are utilizing comprehensive, university-level lecture slides and transcripts developed by Dr. Adriana Simon Coutinho.
Yeah, from the Department of Microbiology, Immunology, and Parasitology at the Federal University of Rio Grande do Sul, or UFRGS, down in Brazil.
Right. It's fantastic material.
Consider this your masterclass. We're going to treat this material with the depth it deserves, exploring not just what happens, but the exact underlying why and how of these cellular mechanisms. So whether you're trying to understand a diagnosis or studying for a medical exam, or you're just insanely curious about the battleground inside your own body, get comfortable.
Absolutely.
Let's officially start with Module 1, Foundations of Carcinogenesis. Because when we hear the word cancer, society often talks about it as if it's one single monolithic monster.
Right, like a singular entity that needs a singular cure.
Yeah, but biologically speaking, that framework is fundamentally flawed, isn't it?
Oh, it is a massive misconception. From a clinical and biological standpoint, cancer is not one disease. It's a broad umbrella term encompassing a collection of over 100 distinct diseases.
Over 100, wow.
Yeah. They originate in different tissues, they rely on different mutations, and crucially, they require entirely different therapeutic approaches.
Which immediately shatters that popular notion of a silver bullet cure for cancer. I mean, you wouldn't expect one antibiotic to cure every single bacterial infection on Earth.
Exactly. But despite their differences, these 100-plus diseases share a devastating global impact. Based on the UFRGS data, we are looking at roughly 20% of all deaths globally.
That's huge.
It is, with around 6 million new cases emerging every single year.
So if they are so different, what's the biological through line? What universally makes a cancer a cancer?
The defining, unifying characteristic across all of them is the formation of an abnormal tissue mass characterized by autonomous growth.
Autonomous growth. Let's unpack that for a second. What does that actually look like at the cellular level?
Think of a normal, healthy cell as a well-behaved citizen in a highly organized, densely populated city. It only divides and replicates when it receives very specific external signals telling it to do so.
Like if I get a paper cut.
Perfect example. If you cut your skin, the surrounding cells receive chemical signals instructing them to multiply and repair the breach. But just as importantly, once the gap is filled, the cells bump into each other.
Oh, right. Physical contact.
Yes, physical contact triggers regulatory, inhibitory signals. The cells realize the neighborhood is crowded and they stop dividing.
So a healthy cell respects the neighborhood zoning laws. It listens to the stoplights. The cancer cell, I assume, just completely ignores them.
It goes much further than ignoring them. The cancer cell often actively destroys its own internal brakes. It jams the gas pedal to the floor. It proliferates entirely independently of exogenous stimuli.
Wow.
It becomes completely deaf to those regulatory inhibitory signals from its neighbors. And furthermore, it usually divides at a highly accelerated rate compared to normal tissue.
But wait, normal cells have a built-in failsafe for this, don't they?
Yeah.
Like if a cell starts acting erratically or sustains massive genetic damage, it's supposed to initiate a self-destruct sequence.
Yes, that process is called apoptosis, or programmed cell death.
Right, apoptosis.
It's a beautifully altruistic mechanism where a damaged cell sacrifices itself. It cleanly dismantles its own internal components so macrophages can clear it away without causing massive inflammation.
All for the good of the broader organism.
Exactly. But a hallmark of cancer is that it develops specific mechanisms to entirely avoid apoptosis. The cell becomes functionally immortal, refusing to die even when its internal sensors detect catastrophic genetic damage.
Okay, so if you have these immortal, rapidly dividing cells just stacking up on top of each other, they're going to need resources. They can't just grow infinitely in a vacuum.
Right. Which brings us to the next critical capability of a tumor, angiogenesis.
Angiogenesis, building blood vessels.
Precisely. A localized cluster of tumor cells cannot grow much larger than a couple of millimeters without establishing its own dedicated blood supply. It needs oxygen and nutrients, and it needs to remove its own metabolic waste.
So how does it get them?
The tumor begins secreting specialized chemical signals, most notably vascular endothelial growth factor, or VEGF. Yeah. These signals essentially coax the body's existing blood vessels to sprout new branches and grow directly into the tumor mass.
So the tumor literally tricks the body into building private supply lines directly to the enemy base.
It forces the host to feed it, and once those vascular supply lines are established, it opens the door to the most dangerous characteristic of all, metastasis.
Ah, right. The spread.
Yes. The malignant cells acquire the ability to detach from their original site, degrade the surrounding connective tissue, and invade the lymphatic system and blood vessels. They travel through these fluid highways to colonize distant tissues, setting up secondary tumors throughout the body.
Okay, so we have this terrifying checklist. Autonomous growth, ignoring stop signals, avoiding the apoptosis self-destruct, building private blood vessels with VEGF, and invading foreign tissues via metastasis.
That's the profile, yeah.
The obvious question is, how does a normal, rule-following cell suddenly acquire all these villainous superpowers?
Well, it all comes down to the molecular basis of carcinogenesis. Cancer arises from genetic mutations. Specifically, it's driven by an accumulation of mutations in the cell's DNA.
And where did these mutations come from?
They can occur in somatic cells, meaning your regular body cells that acquire damage over a lifetime from environmental factors, or they can be present in the germline, meaning the mutations are inherited genetically from a parent.
Now, the source material places a huge emphasis on this concept of monoclonality. And I want to highlight this because it really changed how I visualize a tumor.
It's a crucial concept.
Yeah, because we often imagine cancer as a whole section of an organ suddenly deciding to turn bad all at once, like an entire office of workers spontaneously deciding to rebel on a Tuesday.
Right.
But monoclonality means it starts with just one rogue copy machine. A single cell acquires a flawed original document, a critical mutation. It copies that flaw to its two daughter cells. Those two copy to four, and so on.
Yes.
So the entire resulting tumor, millions of cells, descend entirely from that one single rebellious cellular ancestor.
That analogy perfectly captures the multi-step nature of carcinogenesis, because a single genetic mutation almost never causes cancer on its own.
Really? Just one isn't enough?
Rarely. Our bodies have too many redundant safety systems. It is the steady accumulation of successive mutations over time within that specific clonal lineage that drives tumor progression. With each new division, the offspring acquire new malignant traits until they cross the threshold into full-blown cancer.
But the mutations can't just be anywhere in the DNA, right? I mean, if a cell mutates the gene for eye color, that doesn't cause cancer. What are the specific targets? What genes actually have to break for this cascade to start?
That's the key question. There are 4 very specific classes of target genes that, when mutated, drive carcinogenesis. The first class are the proto-oncogenes.
Proto-oncogenes, okay.
In a healthy cell, proto-oncogenes are your normal growth promoters. They code for the proteins that push the cell through the division cycle when it's appropriate. But when a proto-oncogene mutates, it becomes an oncogene, a hyperactive, permanently activated growth promoter.
That's the jammed gas pedal we talked about. The cell is constantly being flooded with divide, divide, divide signals.
Exactly. What's the second class?
Oh, I'm guessing the brakes.
You got it. The tumor suppressor genes. These act as the crucial brakes. They produce proteins that inhibit cellular growth or halt the cell cycle to allow for repairs. If a mutation inactivates a tumor suppressor gene, the cell loses its ability to stop dividing, even when it should.
The UFRGS material highlights a very specific, famous tumor suppressor gene here, P53. Let's dig into that because it seems foundational.
P53 is huge. It's often referred to as the guardian of the genome, and for good reason. It operates as a critical checkpoint protein, particularly at the transition between the G1 and S phases of the cell cycle.
So right before the cell copies its DNA.
Yes, before a cell is allowed to copy its DNA, P53 inspects the genetic material for damage. If it finds a break or an error, P53 halts the cell cycle and summons repair proteins.
And if it can't fix it?
If the damage is too severe to fix, P53 triggers that apoptosis self-destruct sequence we discussed earlier.
So it's the ultimate quality control inspector. It stops the assembly line if the product is defective. But if P53 itself is mutated,
The assembly line never stops. The damaged DNA is copied, errors and all, passing those mutations down to the daughter cells. And the UFRGS slides note a staggering statistic here.
what is it?
The P53 gene is mutated in approximately 50% of all human tumors.
Wait, really? Half?
Half of all cancers share this specific broken break, allowing genetic chaos to proliferate unchecked.
That is profound. Okay, we have oncogenes pushing the gas, tumor suppressors like P53 losing the brakes. What are the third and fourth targets?
The third class are the genes that specifically regulate apoptosis. If these genes mutate, the cell becomes functionally immune to its own self-destruct mechanisms.
And the fourth,
The fourth and final class are the DNA repair genes.
which makes brutal logical sense. If the DNA repair genes mutate, the cell loses its ability to fix new mutations as they occur.
Exactly. It completely destabilizes the genome, accelerating the rate at which the cell acquires even more errors in the other three classes of genes. It's a compounding cascade of instability.
Now, depending on which specific tissue type this single rogue mutated cell originates from, the medical community classifies malignant tumors into different broad categories.
Yes. Let's map out that classification.
And the distinction between benign and malignant is key here too. Benign tumors stay put, malignant ones invade. But when they are malignant, how do we group them?
The first major category are the sarcomas. These originate in mesenchymal tissue.
Mesenchymal. What does that mean in plain English?
You can think of mesenchymal tissue as the structural supportive components of the body. So bone, muscle, cartilage, fat, and connective tissue. Sarcomas are relatively rare, but they can be quite aggressive.
And the second group, which I believe is the most common.
The carcinomas. These originate in epithelial tissue. Epithelial tissue is the protective layer that lines the surfaces and cavities of your body.
So like our skin.
Skin, yes. Also the lining of your intestine, your oral cavity, the inside of your lungs, breast tissue ducts, the colon, the bladder, the prostate, all epithelial.
Why are carcinomas so much more common than sarcomas?
Two main reasons. First, epithelial tissues are constantly dividing to replace cells that are shed or damaged by friction and exposure. Think of the lining of your gut or your skin. More division means more chances for a copying error to occur.
That makes sense.
Second, these tissues are on the front lines. They are the tissues most directly exposed to environmental insults. UV radiation on the skin, inhaled carcinogens in the lungs, dietary toxins in the colon.
Okay, so sarcomas and carcinomas. What's the third major classification?
Hematopoietic or lymphoid tumors. These originate in the blood-forming tissues of the bone marrow and the cells of the immune system itself.
So this is where leukemias fall.
Yes. This group includes leukemias, which generally involve the overproduction of abnormal white blood cells that circulate throughout the bone marrow and peripheral blood. It also includes lymphomas, which form solid tumors in the glands and nodes of the lymphatic system.
We've touched on environmental insults, but let's dive deeper into etiology. What actually pulls the trigger? What causes that very first mutation that eventually cascades into cancer?
The etiology is inherently multifactorial. Heredity plays a role, providing a genetic predisposition where someone might be born with one mutated copy of a tumor suppressor gene already.
So they're already one step closer.
Exactly. Then you have chemical carcinogens, like the polycyclic aromatic hydrocarbons in cigarette smoke, which directly bind to and distort DNA. Physical radiation from UV sunlight to ionizing radiation physically severs the DNA double helix.
Right.
But the UFRGS source material provides a massive clinical anchor on biological pathogens, specifically viral etiologies.
Viruses causing cancer.
Hmm.
We don't usually associate catching a virus with developing a tumor. Let's unpack the specific ones Dr. Coutinho highlights, and more importantly, how they actually do it.
The source divides them into DNA viruses and RNA viruses. Among the DNA viruses, human papillomavirus, or HPV, is the classic, most well-understood example.
Right, HPV.
There are many strains of HPV, some just cause simple benign warts, but the high-risk strains, particularly HPV-16 and HPV-18, are the primary causative agents of cervical cancer.
How does a virus that causes warts pivot to causing cervical cancer?
It comes down to two specific viral proteins called E6 and E7.
E6 and E7. Got it.
When high-risk HPV infects a cervical cell, it integrates its own viral DNA into the human host's genome. It then produces these E6 and E7 proteins. E6 actively targets and degrades our guardian protein, P53.
Ooh, it takes out the brakes?
Exactly. And E7 binds to and neutralizes another critical tumor suppressor called the retinoblastoma protein, or ARB. The virus literally physically dismantles the cell's two most important brake pedals, so the cell will divide rapidly, creating a factory to produce more viruses.
But this unchecked division, minus the P53 quality control, eventually spirals into malignancy. The virus engineers the environment for its own replication, and the cancer is almost a tragic side effect of that sabotage.
Perfectly stated.
What other DNA viruses are linked to cancer?
Hepatitis B virus, or HBV, is strongly linked to hepatocellular carcinoma, a primary liver cancer. Chronic HBV infection causes constant inflammation, cell death, and rapid regeneration in the liver, drastically increasing the mutation rate.
Okay, HBV. What else?
Then there is the Epstein-Barr virus, EBV.
EBV. Wait, that's the virus that causes mononucleosis, right? The kissing disease.
It is. The vast majority of the population is infected with EBV, and it remains dormant in our B cells forever. But in certain contexts, particularly linked to geographic and genetic cofactors, EBV is the driving force behind several severe malignancies.
Like what?
Burkitt's lymphoma, nasopharyngeal carcinoma, and certain aggressive B-cell lymphoproliferative diseases.
Wow. The source also points out HHV8.
Human herpes virus. This virus is the definitive causative agent of Kaposi's sarcoma, a cancer that causes distinct lesions on the skin and internal organs.
Right, I've heard of Kaposi's sarcoma in relation to the AIDS epidemic.
Yes. What's clinically crucial about HHV8 is that it rarely causes cancer in individuals with a healthy immune system. It overwhelmingly presents in patients who are severely immunodeficient, such as those with advanced, untreated HIV/AIDS or transplant patients on heavy immunosuppressive drugs.
Let's not forget the RNA viruses before we move on.
Right. The primary RNA virus highlighted in the lecture is HTLV1, the human T lymphotropic virus type 1. Unlike the DNA viruses, HTLV1 is a retrovirus, meaning it uses an enzyme called reverse transcriptase to turn its RNA into DNA, which it then inserts into the host's genome.
Oh, like HIV does.
Yes, exactly like that. This insertion can disrupt normal gene function and, over decades of latent infection, lead to adult T-cell leukemia and lymphoma.
You know, that link you mentioned earlier between Kaposi's sarcoma and immunodeficiency opens up a massive conceptual door for us. It brings up the demographics of cancer susceptibility. Who gets cancer the most?
Demographically, we see a massive spike in incidence rates among the elderly. And based on what we've just discussed about the multi-step nature of carcinogenesis, this is entirely logical.
It just takes time.
Right.
Yeah.
It takes time, often decades, for a single cell lineage to accumulate the specific, perfect storm of mutations required in oncogenes, tumor suppressors, and DNA repair genes. The longer you live, the more environmental insults you endure and the more random copying errors stack up.
Makes sense.
We also see specific, distinct peaks in childhood, but these primarily relate to specific leukemias and embryonic tumors where the rapid cell division of development goes awry.
But the truly revealing demographic, the one that bridges us to the next phase of our exploration, is the immunosuppressed population.
It's a massive clinical red flag. Individuals suffering from primary inherited immunodeficiencies or secondary acquired immunodeficiencies, like those with HIV or those taking drugs to prevent organ transplant rejection, they show a drastically higher incidence of certain cancers.
Like the ones we just mentioned?
Yes.
Yeah.
Specifically, they suffer from exponentially higher rates of lymphomas, liver cancer, skin cancers, and cervical cancer.
And this is the pivot point. If people with compromised immune systems get significantly more cancer, that implies something profound. It implies that a healthy immune system is actively fighting off tumors all the time.
Exactly.
It implies that cancer isn't just a failure of cell division, it's a failure of immune recognition. How does our body's internal security force actually recognize and fight this rebellion?
Which is a perfect segue.
Let's officially launch into Module 2. Immune response to tumors. So to synthesize really quickly, Module 1 established that cancer is this progressive cellular rebellion driven by mutations. Now, in Module 2, we ask how our internal security handles it.
The overarching theory you're describing is known as immunosurveillance. It was a hotly debated concept for decades, actually, but it is now the foundational bedrock of tumor immunology.
What does the theory say?
The theory posits that our immune system constantly patrols the body, acting as a surveillance network that identifies and eliminates newly transformed early-stage malignant cells long before they can organize into a clinically detectable tumor.
Beyond the fact that immunodeficient patients get more cancer, what is the concrete experimental proof that immunosurveillance is real?
The source material highlights several vital pieces of evidence. On a clinical level, we occasionally witness the phenomenon of spontaneous regressions.
Like the tumor just disappearing.
Yes. While exceptionally rare, there are well-documented medical cases where highly aggressive tumors, such as certain melanomas or neuroblastomas, simply shrink and vanish without any therapeutic intervention.
Wow. Why?
The biological explanation is that the immune system, perhaps triggered by a concurrent infection, suddenly woke up, recognized the tumor, and unleashed a massive successful attack.
That's the clinical observation, but what about the laboratory? Can we prove the immune system sees the cancer?
Absolutely. Laboratory assays routinely isolate tumor-specific antibodies and tumor-reactive cytotoxic T cells circulating in the peripheral blood of cancer patients. The immune system is unequivocally sensing the presence of the tumor and trying to mount a response. It's just often overwhelmed or suppressed by the time the cancer is diagnosed.
Right. And there were classic animal experiments too, right?
Yes, classic experimental proofs in animal models cemented this. If you take tumor cells, irradiate them so they can't divide, and inject them into a healthy mouse.
Kind of like a vaccine.
Exactly. That mouse effectively becomes vaccinated. If you later inject that same mouse with live virulent cells of that exact same tumor, the mouse's immune system will reject and destroy them completely. It proves immune memory and specific targeting.
Okay, so let's break down the armory. To understand this war, we need to understand the troops. The immune system is broadly divided into two main branches: the innate system and the adaptive system. How do they compare when they're deployed against a tumor?
We need to use some comparative reasoning here to see how they complement each other. The innate immune system is your rapid response force. It's evolutionarily ancient, and crucially, it does not require prior training or exposure to recognize a threat.
It just acts.
Right. It responds to general, broad signs of cellular distress, damage, or abnormal protein patterns.
Who are the key players on the innate side in this context?
In the context of tumor immunology, the innate response relies heavily on activated macrophages and neutrophils. These are phagocytic cells, meaning they physically engulf and digest abnormal or dying tumor cells.
Pac-Man cells.
Basically. The innate side also involves the complement system, which is a complex cascade of proteins circulating in the blood that can spontaneously assemble into weaponized complexes that punch holes in abnormal cell membranes.
Good role.
But arguably, the most fascinating player on the innate side is the natural killer cell, or NK cell.
Natural killer cells. It sounds like something out of an action movie.
They absolutely live up to the title. NK cells are specialized lymphocytes that are pre-programmed to detect and execute stressed, virally infected, or malignant cells.
And they do this without needing the adaptive system's help.
Mostly, yes. They do it without needing the specific, highly targeted antigen recognition that the adaptive system requires. They operate on a balance of activating and inhibitory signals, which we will explore deeply when we discuss evasion.
Now, contrast that innate rapid response force with the adaptive immune system.
The adaptive immune system is your highly trained, specialized Special Forces command. It takes days or even weeks to fully deploy, but its precision is unmatched.
Because it's targeted.
Highly targeted. It doesn't react to general distress. It targets incredibly specific, unique molecular markers on the tumor cells called antigens. The primary operators here are the CD4 positive helper T cells, the CD8 positive cytotoxic T cells, and the B cells, which are responsible for manufacturing antibodies.
This is where we need to dive into the mechanistic depth. Because if the innate system is the first on the scene, and the adaptive system is the heavy artillery that arrives later, they have to communicate. The innate system has to hand the intelligence over. How does that handoff actually happen?
That intelligence handoff is the primary job of the dendritic cell. You can think of dendritic cells as the ultimate intelligence officers and sentinels of the immune system.
Okay, I'm tracking.
They reside deep within our tissues, constantly sampling their environment. When a dendritic cell encounters a developing tumor, it will ingest parts of the dead, dying, or abnormal tumor cells.
It gathers the evidence.
Exactly, but it doesn't just hold on to it. The dendritic cell processes those ingested tumor proteins, chopping them up into tiny, highly specific fragments. These fragments are the antigens.
Right.
The dendritic cell then leaves the tissue, enters the lymphatic system, and travels directly to the nearest lymph node.
The command center.
Once inside the lymph node, the dendritic cell displays these chopped up tumor antigens on its outer surface, holding them up like a highly specific mugshot.
I love that visual.
It uses specialized molecular display trays to do this, called major histocompatibility complex, or MHC molecules. Specifically, to activate the adaptive response, it presents these antigens to naive CD4 positive helper T cells using MHC class II molecules.
MHC class 2 for CD4.
Got it. And it presents to CD8 positive cytotoxic T cells using MHC class I.
But wait, I remember a crucial detail about this interaction from the slides. The T cell can't just look at the mugshot and immediately launch an attack, right? There's a safety mechanism built in to prevent accidental friendly fire.
You're referring to the co-stimulatory signal, and it is a brilliant evolutionary failsafe. For a T cell to fully activate, simply recognizing the antigen in the MHC tray is not enough. That's just key number one.
What's key number 2?
To turn the engine on, the dendritic cell must simultaneously present a second molecule on its surface, a co-stimulatory molecule like B7. This B7 molecule must lock into a specific receptor on the T cell called CD28.
It's a 2-key verification system.
Right.
Like launching a nuclear submarine, the officer and the captain both have to turn their keys at the exact same time. Why is that so important?
Because the weapons these T cells deploy are incredibly destructive. If a T cell accidentally recognized a normal healthy protein and launched an attack, you would develop a catastrophic autoimmune disease where your body destroys its own organs.
Oh, wow.
The 2-key system ensures that the T cell only activates when it sees the specific antigen, and it receives confirmation from the dendritic cell that, yes, this antigen was found in a context of danger and tissue damage.
Okay, so the 2 keys are turned. MHC binds the T cell receptor. B7 binds CD28. The CD4 positive helper T cell is officially activated. What does it do? It's called a helper, so I assume its job is logistics and command, not necessarily hand-to-hand combat.
Spot on. The activated CD4 helper T cell orchestrates the entire massive counterattack by synthesizing and releasing powerful chemical messengers called cytokines.
Cytokines.
Yes, these cytokines are broadcast into the environment to mobilize and upgrade the rest of the immune army. They activate B cells, instructing them to differentiate and start mass-producing antibodies perfectly tailored to bind to that exact tumor antigen.
Right.
They activate nearby macrophages, transforming them from passive garbage collectors into hyper-aggressive tumor killers. And critically, they regulate and support the full activation of the CD8-positive cytotoxic T cells.
The CD8 cells are the actual assassins of the adaptive system.
Yes. Once fully activated by the dendritic cells and supported by the helper T cell cytokines, the CD8 cells leave the lymph node, hunt down the specific cells bearing that tumor antigen, and induce apoptosis directly by injecting lethal proteins called perforins and granzymes.
Let's look closer at those chemical messengers, the cytokines. Dr. Coutinho highlights 3 very specific ones in the curriculum that dictate this battle. What are they?
The first, and arguably the most critical for expansion, is interleukin-2, or IL-2.
IL-2.
IL-2 is the primary growth factor for T cells. Once a T cell is activated by the 2-key system, it absolutely requires IL-2 to undergo clonal expansion, to rapidly divide and create an army of millions of identical clones, all programmed to hunt that specific tumor. IL-2 is also a potent stimulator for the division and activation of natural killer cells.
So IL-2 is the signal to build a massive army. What's the second?
Interferon gamma, or IFN gamma. This cytokine is the ultimate macrophage activator. When macrophages are exposed to IFN gamma, their tumoricidal activity skyrockets. They become highly aggressive, their internal digestion mechanisms become more lethal, and they become highly efficient at engulfing and destroying tumor cells.
And the third cytokine.
Tumor necrosis factor alpha, or TNF alpha.
Sounds intense.
As the name implies, it was discovered based on its ability to induce the necrosis or death of tumors. TNF-alpha induces severe local inflammation, alters the blood vessels to allow more immune cells to enter the tissue, and it directly increases the lytic capacity, the raw killing power of the CD8-positive T cells.
So we have macrophages eating cells, CD8 T cells injecting lethal proteins, but we also mentioned B cells churning out antibodies. Now, we all know antibodies are great at neutralizing tiny viruses, keeping them from entering our cells. But how does an antibody kill a massive tumor cell? It can't just smother it.
It doesn't smother it, it marks it for execution. This is where we see one of the most elegant, highly coordinated mechanisms in tumor immunology, a process called antibody-dependent cellular cytotoxicity, or ADCC.
ADCC. This is a mechanism that completely changes how you view antibodies. Let's break this down sequentially.
First, the activated B cells manufacture millions of antibodies specifically engineered to match the tumor's surface antigens. These antibodies flood the bloodstream, enter the tumor microenvironment, and physically bind to the antigens protruding from the surface of the malignant cells.
Think of it like modern targeted warfare. The tumor cell is an enemy bunker hidden in the jungle. The antibodies are not the bombs. They are the laser designators. They fly in and attach themselves to the target, painting it with a highly visible molecular laser.
I like that visual. So the target is painted. What drops the bomb?
Who are eyes?
Enter the natural killer cells, along with certain other cells like eosinophils and macrophages. NK cells possess a highly specific receptor on their surface called the Fc gamma RI receptor. In clinical terms, we often just call it CD16.
CD16. And the sole purpose of this CD16 receptor is to look for the laser.
Precisely. Antibodies have a Y shape. The tips of the Y bind to the tumor antigen. The stem of the Y, called the Fc portion, sticks out. The CD16 receptor on the NK cell is perfectly contoured to recognize and grab onto that protruding Fc tail of an antibody.
So the NK cell is essentially a guided missile strike patrolling the body. It doesn't fire randomly. It only locks on and activates when its CD16 receptor senses the tail of an antibody that has successfully painted a target.
And it requires multiple conformations. Multiple CD16 receptors on the NK cell must bind to a dense cluster of antibodies coating the tumor cell. This clustering is called cross-linking.
Cross-linking confirms the lock-on.
Yes. Once cross-linking occurs, the lock-on sequence is confirmed. The NK cell is flooded with activating signals. It presses right up against the tumor cell, forming what we call an immunological synapse, and unleashes lethal granules directly into the gap between them.
And what's in those granules?
Perforin, which literally punches physical holes into the tumor cell's membrane, and granzymes, which enter through those holes and trigger the irreversible cascade of apoptosis. The painted target is completely destroyed.
Yeah.
And as a brief add-on, those same antibodies painting the target can also trigger the classical complement pathway, where blood proteins assemble into a literal drill, the membrane attack complex that ruptures the tumor cell independently of the NK cells.
When you lay it all out like this, the immune system sounds invincible. We have dendritic cells gathering intelligence, the two key failsafe, IL-2 building massive clone armies, macrophages turning hyper-aggressive, CD8 assassins, and NK cells dropping guided munitions via ADCC. It is a breathtaking, multi-layered assault.
It truly is.
Which brings us to the most frustrating, agonizing question in all of oncology. If our immune system is this sophisticated, this heavily armed, how does cancer ever win? How do our tumors survive day one?
That paradox is the dark heart of tumor immunology. And to understand it, we must transition to studying the evasion mechanisms. We have to look at how cancer fights back.
Which means it's time to officially announce Module 3, Evasion Mechanisms. Let's synthesize Module 2 for a second. Our immune system has this incredible arsenal: antibodies, T cells, NK cells. Now, how does a tumor possibly survive this onslaught? What are the dark arts of tumor survival?
To frame this battle, immunologists use a concept known as the 3 E's of cancer immunoediting. They represent the 3 phases of the interaction between the tumor and the immune system: elimination, equilibrium, and escape.
Let's walk through them. Elimination is phase 1.
Elimination is everything we just discussed. This is the ideal scenario, and it happens inside your body constantly. A cell acquires dangerous mutations, it begins to act abnormally, the innate and adaptive systems recognize the threat, and they entirely clear the malignant cells. The tumor is eliminated before it ever becomes a problem.
But the system isn't perfect. Sometimes a handful of cells survive the initial barrage.
Which plunges us into the second E equilibrium. The immune system hasn't cleared the tumor, but the tumor isn't growing rapidly either. Because these tumor cells have broken DNA repair genes, they are genetically unstable. They are constantly mutating, dividing, and creating a highly heterogeneous, diverse population of cells.
And this is where the concept of microevolution becomes terrifying. Because the immune system doesn't stop attacking. It is constantly killing off the vulnerable tumor cells.
Exactly. The immune system is applying massive evolutionary pressure. It acts as the ultimate predator. By systematically slaughtering all the tumor cells that are highly visible and vulnerable, the immune system is unwittingly selecting for the rare, randomly mutated tumor cells that happen to possess traits that make them invisible or resistant to the immune attack.
So it's Darwinian natural selection playing out over months or years within a single millimeter of tissue.
Yes. The immune system forces the tumor to become stronger by killing the weak ones. And once a tumor cell acquires the perfect combination of evasive mutations, we cross the threshold into the final E. Escape. The tumor breaks free of immune control. It has acquired the camouflage and the defensive weaponry necessary to completely ignore the immune system, allowing it to proliferate wildly and cause clinical disease.
So what exactly are these evasive maneuvers? What kind of camouflage does a tumor use to become invisible to that massive arsenal we just detailed?
The most direct method is simply hiding in plain sight through low immunogenicity. A tumor cell might randomly mutate the gene that produces the specific surface antigen that the T cells and antibodies are targeting. If the antigen disappears, the target disappears.
That's pretty straightforward.
Or alternatively, some tumors physically shed their surface antigens in massive quantities, releasing them into the surrounding tissue fluid.
What does shedding them accomplish?
These free-floating shed antigens act as molecular decoys. The circulating antibodies and T cells bump into these floating fragments, bind to them, and expend their energy on harmless garbage long before they ever reach the actual surface of the tumor cell.
It's like deploying a massive smokescreen. But there is a more active, dynamic version of this too, right? Something called antigenic modulation.
Antigenic modulation is a brilliant reactive defense. It is a process where the immune system's attack actually teaches the tumor to hide. Let's say a B cell produces a perfect antibody that successfully binds to a specific antigen on the tumor's surface.
Okay.
The tumor cell's internal machinery physically senses this binding event. In response to being tagged, the tumor cell actively endocytoses. It swallows that entire section of its own membrane, pulling the antigen and the attached antibody inside the cell, where it degrades them in a lysosome.
That is wild. The act of painting the target causes the tumor to pull the target inside and lock the door.
And the tumor then selectively downregulates the expression of that specific antigen. The immune system essentially trained the tumor to stop displaying its vulnerabilities.
Okay, that deals with antibodies.
Yeah.
But what about the CD8 cytotoxic T cells?
Yeah.
They don't use antibodies. They rely on looking at those MHC class I molecules to see if the internal proteins are mutated.
This requires us to apply some comparative reasoning to understand the tumor's next move and the immune system's countermove. As we established, CD8 positive T cells absolutely fundamentally require the presence of MHCI molecules to recognize and kill a tumor cell.
The MHCI is the display window.
Yes.
Yeah.
If you want to hide what's going on inside the factory, what do?
You board up the windows.
Exactly.
Uh,
A highly common, incredibly effective evasion strategy is for the tumor to mutate the genes responsible for manufacturing or transporting MHCI. The tumor cell completely stops expressing MHCI on its surface. To the CD8 T cells, that tumor cell just became completely invisible. It literally has no way to interface with it.
It throws away its ID badge so the security guards can't check it. But you mentioned earlier that the immune system anticipated this exact move.
It did, and this is where the natural killer cells act as the ultimate biological failsafe. NK cells operate on an inverted logic compared to T cells. They do not require MHCI to activate.
Oh, right.
In fact, their innate killing instinct is normally inhibited by the presence of healthy, normal MHCI molecules. When an NK cell bumps into a normal cell, the MHCI binds to an inhibitory receptor on the NK cell, sending a signal that says, "Don't shoot, I belong here."
So when the tumor cell boards up the windows and stops expressing MHCI to hide from the T cells,
It removes the primary inhibitory signal that was holding the NK cells back. The NK cells are triggered to kill specifically by the absence of MHCI.
That is a brilliant evolutionary trap. If you drop your ID badge to sneak past the guards, the security cameras are programmed to flag anyone without an ID badge immediately. And the source material talks about a specific experiment that proved this NK cell failsafe.
Yes, Dr. Coitino's material highlights classic experiments utilizing nude mice. These are laboratory mice that have a genetic mutation resulting in an absent or severely deteriorated thymus.
And the thymus is where T cells mature.
Precisely. Because T cells mature in the thymus, these mice possess almost zero functional T cells. Under normal logic, you would expect these nude mice to be completely, utterly defenseless against any tumor, since they lack the heavy artillery of the adaptive system.
But that's not what happened.
Not at all. When researchers injected these nude mice with specific tumor cells that actively lacked MHCI expression, the nude mice were actually able to control and reject the tumor growth surprisingly well.
Because even though they had no T cells, their innate NK cells recognized the missing MHCI and immediately went to work. It's a beautiful system. But wait, we know tumors eventually achieve the escape phase, so if dropping MHCI alerts the NK cells, the tumor must have evolved a way to deal with the NK cells too.
And this brings us to one of the most mechanically fascinating, almost sinister evasion tactics in the entire curriculum.
Yeah.
The MICNKG2D decoy system.
I want to go deep on this one because it sounds like science fiction. Let's map the players first.
Let's start with carcinomas, tumors of epithelial origin. When these epithelial cells undergo malignant transformation and become stressed, they often begin to express a non-classical, stress-induced MHC variant on their surface. The primary one we study is called the MIC protein.
So the tumor is expressing MIC. What recognizes it?
On the other side, we have our natural killer cells and a subset of specialized T cells. These killer cells possess a highly specific, powerful activating receptor called NKG2D.
Okay, so we have the MIC protein on the tumor and the NKG2D receptor on the killer cells. What happens when they meet?
When the NKG2D receptor binds to the MIC protein on the tumor cell, it acts as a massive overriding kill signal. The NK cell locks on, activates, and destroys the tumor cell.
So the tumor expressing MIC is essentially painting a target on its own back. How does it evade this?
By using the target as a weapon. The advanced escaped tumor cell mutates to secrete a specialized enzyme, a protease. This protease acts like a microscopic pair of scissors. It continuously snips the MIC proteins right off the surface of the tumor cell.
So instead of being attached to the cell membrane, the MIC proteins are just severed and floating away.
Yes, they become soluble MIC. And the tumor churns them out in massive quantities, flooding the entire tumor microenvironment with these free-floating MIC proteins.
It's molecular chaff. Like a fighter jet deploying a cloud of burning magnesium flares to blind a heat-seeking missile. The NK cells fly into the area, their NKG2D receptors lock onto the thousands of floating MIC decoys, and the actual tumor cell sneaks away completely unnoticed.
That analogy is highly accurate for the first half of the mechanism, but the biological reality is far more devastating than just distraction. When the NKG2D receptor on the NK cell binds to that soluble decoy MIC, the binding triggers a cellular response. But because the MIC isn't anchored to anything, that NK cell actually endocytoses its own receptor.
Wait, it swallows its own radar dish.
Yes. The entire NKG2D receptor complex, bound to the decoy MIC, is pulled inside the NK cell and completely degraded. The NK cell isn't just distracted for a moment. It is actively, permanently disarmed. It is blinded. When that NK cell eventually bumps into the actual tumor cell, it physically lacks the receptors necessary to recognize the threat. The tumor has engineered the complete localized disarmament of the innate immune system.
That is terrifyingly elegant.
And yet, it gets worse. Tumors do not just hide. They actively engage in chemical warfare to suppress the immune cells around them. They manipulate and control the tumor microenvironment.
Immunosuppression. How do they achieve that locally? We're not talking about systemic HIV here. We're talking about a solid tumor shutting down the immune response in its own neighborhood.
They do it by hijacking the immune system's own off switches. Tumors actively synthesize and secrete potent immunosuppressive cytokines. The two most critical ones highlighted in the UFRGS lectures are transforming growth factor beta, or TGF-beta, and interleukin-10, or IL-10.
What do TGF-beta and IL-10 actually do to the immune cells?
They act as profound chemical suppressants. When nearby dendritic cells, Th1 helper cells, and CD8 cytotoxic T lymphocytes are exposed to high concentrations of TGF-beta and IL-10, their cellular machinery grinds to a halt. The cytokines directly inhibit their activation, block their ability to proliferate, and completely suppress their ability to deploy weapons like perforin. The attackers are paralyzed.
But they don't just paralyze the good guys, do they? Don't these cytokines also actively recruit bad actors to the site?
They recruit the body's own peacekeepers and force them to work for the enemy. Crucially, TGF-beta and IL-10 are the exact chemical signals used to recruit and expand highly specialized populations of immune cells that naturally exist to dampen immune responses. Specifically, they recruit regulatory T cells, or TREGs.
Let's talk about TREGs, because normally TREGs are essential for our survival, right?
Absolutely. Without regulatory T cells, we would all die of rampant autoimmune disease. After a normal infection is cleared, TREGs enter the area and suppress the active T cells to calm the inflammation down and return the tissue to baseline. They are defined by specific molecular markers. They are CD4 positive, CD25 positive, and critically, they express a master transcription factor called FOXP3.
But the tumor hijacks this peacetime mechanism.
The tumor essentially sends out a fake, "the war is over, come calm things down" signal. It recruits massive numbers of these CD4 positive, CD25 positive, FOXP3 positive TREGs into the tumor microenvironment. And once they arrive, these TREGs begin secreting even more TGF-beta and IL-10.
A vicious cycle.
This creates a localized, self-reinforcing, impenetrable fortress of immunosuppression. The tumor builds a moat around itself and mans the walls with hijacked immune peacekeepers.
Are TREGs the only ones they recruit?
No, the source also details the recruitment of myeloid-derived suppressor cells, or MDSCs. These are immature immune cells that, under the influence of the tumor's cytokines, halt their development and instead become highly potent suppressors of T-cell function. Together with TREGs, they completely paralyze any effector immune response trying to penetrate the tumor bed.
The lecture also briefly mentions something called tolerance as an evasion mechanism. What role does tolerance play?
The material notes two specific types of tolerance that allow a tumor to escape: low-dose and high-dose tolerance. They relate to how the immune system perceives antigen concentration.
Okay, what's low-dose tolerance?
Early on, when the tumor is microscopic and shedding very few antigens, the absolute amount of tumor antigen might simply be too low to trigger the activation threshold of the T cells. It flies completely under the radar. That's low-dose tolerance.
And high-dose.
Later in the disease process, when the tumor is massive, the explosive proliferation of malignant cells can dump such a colossal, overwhelming volume of antigen into the system that it completely exhausts the T cells. They become overstimulated and undergo apoptosis themselves, or enter a state of permanent energy, meaning they are alive but functionally paralyzed. That is high-dose tolerance.
Wow. Okay, let's officially transition to Module 4. Diagnosis of tumors. Let me synthesize everything we just learned about evasion, because it changes the whole paradigm of how we view cancer. Tumors are basically master illusionists. They shed their antigens as smoke screens. They swallow their own targets to hide them. They drop their MHC ID badges to blind T cells. They deploy molecular chaff like MIC to disarm NK cells. And they recruit an army of our own peacekeepers to build a wall of suppression.
It's incredibly, terrifyingly sophisticated.
Which presents a monumental, seemingly impossible challenge for doctors. If tumors are this adept at hiding from our own highly evolved internal sensors, how does an oncologist pierce through this illusion in the clinic? How do we find an enemy that is functionally invisible?
Right, and this brings us to the crucial pivot of diagnostics, specifically looking at tumor markers. The clinical diagnosis of cancer relies on a multifaceted array of highly specialized tools designed to detect the structural, cellular, and molecular footprints of the disease.
Like what kind of tools?
Well, histological methods, biopsying the tissue and looking for abnormal shapes under a microscope, those are foundational. But immunology has provided us with a much sharper lens.
Let's talk about that immunological lens. The UFRGS curriculum goes into great detail about tumor markers. First, just define what a tumor marker actually is.
A tumor marker is a biological substance, often a protein, an enzyme, a hormone, or a specific antigen that is produced either directly by the cancer tissue itself or by the patient's body in response to the cancer's growth. We can detect these markers in blood, urine, or tissue samples.
But not all markers are created equal. The lecture draws a very hard line between tumor-associated antigens and tumor-specific antigens. What is the difference?
It's the difference between a clue and a conviction. A tumor-specific antigen is a protein that is produced only by the mutated cancer cells and is absolutely never found on a normal, healthy cell. These are incredibly rare, usually resulting from highly specific viral mutations or unique genetic translocation.
So specific means only the tumor has it. What about associated?
A tumor-associated antigen is a protein that is naturally produced by normal cells in the body, but is produced in drastically higher abnormal quantities by the cancer cells.
So a specific antigen means cancer, 100%.
Yeah.
An associated antigen means something is wrong. It might be cancer, but it could be inflammation.
Exactly. And practically all the clinical tumor markers we use in daily practice are tumor-associated, not tumor-specific.
Which means they aren't perfect. The source outlines the criteria for an ideal tumor marker. What would the holy grail of markers look like?
An ideal tumor marker would be 100% highly specific, meaning it is only elevated if cancer is present, zero false positives from benign conditions. It would be 100% highly sensitive, meaning it detects every single case of the cancer, even at microscopic stages, zero false negatives. And its level in the blood would correlate perfectly with the exact size and stage of the tumor mass.
Does this ideal marker exist?
No, not a single marker currently in clinical use meets all those criteria.
None of them.
None. They all have limitations, which is why we must use them strategically. They are rarely used alone for primary screening. They are primarily used to aid in diagnosis alongside imaging and biopsies to monitor a patient's response to treatment, like if the marker level drops, the chemotherapy is working, and crucially for surveillance, to detect a recurrence of the tumor months or years before it shows up on a CT scan.
Let's anchor this in clinical reality. Let's look at one of the most famous tumor markers in the world, one that many of you listening have probably seen on a blood test report. PSA, prostate-specific antigen. How does this fit into what we just discussed?
PSA is a perfect case study. It stands for prostate-specific antigen, but that name is a bit misleading. It is specific to the prostate gland, but it is not specific to prostate cancer.
Oh, interesting.
Yeah, PSA is a normal glycoprotein produced by the epithelial cells of the prostate to help liquefy semen. Every single healthy male has PSA in their blood.
So why do we test for it?
Because when the architecture of the prostate gland is disrupted by a growing tumor, the cancer cells leak massive amounts of PSA into the bloodstream. A highly elevated PSA is a massive red flag for prostate cancer.
But here's the problem with specificity. The prostate architecture can also be disrupted by benign conditions, right?
Exactly. Benign prostatic hyperplasia, or BPH, which is just the normal enlargement of the prostate as men age, will elevate PSA. Prostatitis, an infection or inflammation of the prostate, will spike PSA levels dramatically.
So a high PSA doesn't guarantee cancer. It just guarantees prostate distress. How do doctors differentiate between BPH and actual cancer using just this blood test?
By looking at the molecular state of the PSA in the blood, PSA exists in two forms: bound to other proteins or floating freely.
Okay.
For complex biochemical reasons, patients with benign conditions like BPH tend to have a higher percentage of free PSA in their blood. Patients with actual prostate cancer tend to have a much lower percentage of free PSA, with most of it bound to proteins. So oncologists don't just look at the total PSA number. They analyze the ratio of free to total PSA to sharpen their diagnostic accuracy and decide if a physical biopsy is necessary.
That is fascinating. It's not just the presence of the marker. It's the specific biochemical state of the marker. Now, the curriculum lists an absolute alphabet soup of other essential markers. Let's run through them because this is the real detective work of oncology. Let's start with AFP.
AFP stands for alpha-fetoprotein. This is a protein normally produced by the yolk sac and liver of a developing fetus. In healthy adults, levels should be practically zero.
And if they spike?
If AFP levels spike in an adult, it is a primary marker for hepatocellular carcinoma, liver cancer, and non-seminomatous germ cell tumors of the testicle.
But because it's associated with fetuses, I imagine it has applications in pregnancy too.
It does. In obstetrics, measuring AFP in the mother's blood or amniotic fluid is crucial. Elevated levels can indicate neural tube defects like spina bifida in the fetus, while abnormally low levels can be an indicator of Down syndrome.
Incredible dual use. Next on the list is CEA.
Carcinoembryonic antigen. Similar to AFP, CEA is normally produced during fetal development and shuts off before birth. If it reappears in an adult, it is the primary gold standard marker for monitoring colorectal cancer.
Is it used for screening?
No, it is not sensitive enough to use as a primary screening tool for the general public, but once a patient is diagnosed with colon cancer, measuring CEA levels is the best way to track if the surgery was successful or if the cancer has metastasized to the liver.
Let's move to the CA markers. There's a whole family of these carbohydrate antigens. Let's start with CA15-3.
CA15-3 is primarily used to monitor breast cancer. Again, it is not used for initial screening, that's what mammograms are for, but it is highly effective for monitoring patients with advanced breast cancer to see if they are responding to hormonal therapy or chemotherapy.
Next is CA19-9.
This is a critical marker for pancreatic cancer, as well as cancers of the biliary tract and stomach. Pancreatic cancer is notoriously difficult to diagnose early because the pancreas is hidden deep in the abdomen. CA19-9 helps track the progression of the disease.
And CA125.
CA125 is the premier marker for ovarian cancer, specifically epithelial ovarian tumors. It is also used to monitor endometrial cancer.
Does it have specificity issues?
Severe specificity issues. It can be elevated by benign gynecological conditions like endometriosis, pelvic inflammatory disease, or even normal menstruation.
What about HCG? We usually associate that with home pregnancy tests.
Human chorionic gonadotropin. Yes, it is the hormone that indicates pregnancy produced by the placenta. But in oncology, massively elevated levels of HCG in a non-pregnant woman are diagnostic for choriocarcinoma, a rare but aggressive cancer of the uterus. In men, HCG is a vital marker for certain types of testicular cancer.
Just a few more to cover for complete coverage. What about BTA?
Bladder tumor antigen. This is detected in the urine, not the blood, and is used to monitor for the recurrence of bladder cancer alongside cystoscopy.
NOC.
Neuron-specific enolase. This is an enzyme found in neural tissue. It is a highly specific marker for tumors of neuroendocrine origin, most notably small cell lung cancer, which is a highly aggressive form of lung cancer, often linked to smoking, as well as neuroblastomas in children.
And CA72-4.
A slightly less common marker, but utilized primarily for monitoring gastric or stomach cancer and sometimes mucinous ovarian tumors.
To round out the list from the curriculum, we have PP, CT, and TG.
PPP is prostatic acid phosphatase, an older marker for prostate cancer that has largely been superseded by the much more sensitive PSA test. CT stands for calcitonin, a hormone produced by the thyroid gland. It is the definitive marker for medullary thyroid carcinoma, and TG is thyroglobulin, another thyroid protein, used to monitor patients who've had their entire thyroid removed due to differentiated thyroid cancer. If TG levels start to rise months after the thyroid was surgically removed, it means the cancer has returned.
When you look at this entire toolkit, the blood tests, the molecular probes, the flow cytometry analyzing single cells, it is a testament to human ingenuity. We use the body's own leaked proteins to find tumors that are actively trying to hide from the immune system.
And that realization that we understand the exact molecular interface between the tumor and the immune system leads us to the final, most revolutionary frontier in modern oncology.
Which brings us officially to Module 5, immunotherapy. Let's synthesize. We've defined the enemy's origins. We've mapped our internal innate and adaptive defenses. We've uncovered the tumor's incredibly complex evasion tactics, and we've explored the diagnostic markers we use to track the invisible footprint. We know how it works, how it hides, and how we find it.
The ultimate question is, how do we use this deep granular knowledge of immunology to actually cure the patient?
Exactly, immunotherapy.
Immunotherapy represents a fundamental paradigm shift in how we approach the disease. For the last century, the pillars of cancer treatment were surgery, radiation, and chemotherapy. You can think of them as cut, burn, and poison.
Cut, burn, and poison.
Right. While effective, these therapies are incredibly blunt instruments. They cause massive collateral damage to healthy, rapidly dividing tissues, leading to severe side effects like hair loss, immune suppression, and severe gastrointestinal distress. Immunotherapy asks an entirely different question.
Instead of using external poisons, can we stimulate, train, or genetically engineer the patient's own immune system to overcome the tumor's evasion mechanisms and execute the cancer with surgical precision?
Exactly. And Dr. Coutinho's curriculum highlights the major revolutionary approaches that have moved from the laboratory to the front lines of clinical practice. Let's start with a concept that directly addresses the immunosuppression we talked about earlier, immune checkpoint inhibitors.
This is a concept that won the Nobel Prize. Let's unpack the mechanism. We talked earlier about how the T cell needs two keys to turn on the MHC holding the antigen, and the B7 co-stimulatory molecule binding to the CD28 receptor. That's the gas pedal. How do the brakes work?
T cells are designed to naturally exhaust themselves and turn off after a while to prevent them from destroying healthy tissue once an infection is cleared. They do this by expressing inhibitory receptors on their surface, the two most famous being CTLA4 and PD-1.
CTLA4 and PD-1, these are the brake pedals.
Yes. When CTLA4 binds to that same B7 molecule on a dendritic cell, or when PD-1 binds to a molecule called PDL1 on a tissue cell, it sends a massive stop signal into the T cell. It paralyzes it.
And tumors, being the master adapters they are, figure this out.
Exactly. Tumors exploit this natural braking system. Many tumors mutate to express massive amounts of PD-L1 on their surface. When a perfectly activated, lethal CD8 T cell arrives to kill the tumor simply reaches out with its PD-L1, pushes the PD-1 brake pedal on the T cell, and completely shuts the T cell down. The assassin is put to sleep.
So what do immune checkpoint inhibitors do?
They are brilliant in their simplicity. Checkpoint inhibitors are laboratory-manufactured antibodies drugs like anti-PD-1, anti-PD-L1, and anti-CTLA-4. We inject these antibodies into the patient, and they physically block the interaction. The anti-PD-1 antibody covers up the brake pedal on the T cell. The tumor reaches out to press the brake, but its hand is blocked by the drug. The brake cannot be pressed.
We literally cut the brake lines on the immune system.
Exactly. The T cells wake up from their tumor-induced paralysis, recognize the cancer, and absolutely decimate it. This therapy has resulted in long-term, durable remissions in patients with advanced metastatic melanoma and lung cancers that were previously considered complete death sentences.
It's breathtaking. But checkpoint inhibitors rely on the patient already having T cells that know what the tumor looks like. What if we need to actively train the immune system from scratch? That brings us to dendritic cell vaccines. We talked about dendritic cells as the intelligence officers. How do we turn them into a vaccine?
This is where we see remarkable mechanistic depth in personalized medicine. The goal is to optimize the antigen presentation process outside the suppressive environment of the patient's body. Step 1. The clinical team extracts both a sample of the tumor tissue and a large population of the patient's own naive dendritic cells from their blood.
So we take the intelligence officers out of the war zone.
Step 2 takes place entirely in vitro, in a highly controlled laboratory environment. The extracted dendritic cells are exposed to the pulverized tumor antigens. Free from the tumor's suppressive TGF-beta and IL-10, the dendritic cells highly efficiently endocytose and process these antigens. They are essentially loaded with the specific, highly detailed intelligence of that patient's unique personal tumor.
They're given the enemy dossiers in a safe room.
Step 3. These newly supercharged, fully mature, antigen-loaded dendritic cells are infused back into the patient's bloodstream. They naturally migrate straight to the lymph nodes, and because they are optimally activated, they effectively present the concentrated tumor antigens to the patient's naive T cells.
This bypasses all the low-dose tolerance issues we discussed earlier. It forces a massive, highly specific expansion of cytotoxic T lymphocytes perfectly programmed to hunt down and destroy the tumor. Does it work clinically?
Yes, the source notes this specific autologous cellular therapy has shown clinical success in prolonging survival, particularly for patients with advanced melanoma and some prostate cancers.
Incredible. Now let's talk about the absolute workhorses of modern targeted therapy. The precision weapons we discussed in the ADCC section. Monoclonal antibodies or mAbs?
Monoclonal antibodies represent arguably the most widely utilized and successful form of targeted immunotherapy today. The concept is to use bioengineering to mass-produce identical, highly specific antibodies in a laboratory that are perfectly contoured to bind to one exact tumor marker on the surface of a cancer cell.
The curriculum divides them into two main types, naked mAbs and conjugated mAbs. Let's start with naked. What does a naked antibody do? It's just a protein. It's not inherently toxic, right?
Correct. Naked mAbs are highly specific targeting beacons. When they bind to the tumor marker, they do not inherently kill the cell by themselves. Instead, they act as massive flags to recruit the patient's own immune system, relying entirely on the mechanisms we detailed earlier.
They are the artificial laser designators.
Precisely. The UFRGS curriculum provides a vital list of these naked mAbs and their specific targets. Let's run through the key ones. First is rituximab. It specifically targets the CD20 antigen, which is found on the surface of B cells. It is revolutionary for treating non-Hodgkin lymphomas and chronic lymphocytic leukemias.
But wait, if rituximab targets CD20 and all B cells have CD20, doesn't it wipe out the patient's healthy B cells too?
It does. That is the clinical collateral damage of targeting a lineage marker rather than a purely tumor-specific one. But the body can eventually regenerate healthy B cells from stem cells after the therapy, whereas the leukemia would have killed the patient.
A necessary trade-off. What are the others?
Trastuzumab is arguably one of the most famous. It targets the HER2 receptor, which is overexpressed in about 20% of aggressive breast cancers. By binding HER2, it flags the cell for destruction by NK cells via ADCC. Then we have alemtuzumab, which targets CD52, used for chronic lymphocytic leukemia.
What about carcinomas? Do we have naked antibodies for solid tumors?
Yes, cetuximab and panitumumab both target the epidermal growth factor receptor, or EGFR. These are heavily utilized in treating advanced colorectal cancer and head and neck cancers. By binding EGFR, they not only flag the cell, but they block the growth signals from reaching the tumor. And finally, a very unique naked mAb is bevacizumab.
What makes it unique?
It doesn't target the tumor cell itself. Bevacizumab targets VEGF, vascular endothelial growth factor.
Ah, the chemical signal the tumor uses to build its own blood vessels, the angiogenesis signal.
Exactly. Bevacizumab binds to and neutralizes the VEGF molecules in the bloodstream. It literally starves the tumor by preventing it from building those new supply lines.
That is brilliant. But what if the patient's immune system is so severely suppressed by the tumor microenvironment that even when the naked mAbs paint the target, the NK cells are too exhausted to respond? This is where we bring in the heavy artillery, conjugated mAbs.
Exactly. If the patient's immune cells can't do the job, we use the antibody as a precision delivery vehicle for a lethal payload. Conjugated mAbs are antibodies that have been physically attached in the lab to a highly toxic substance.
The source mentions two types of payloads, radioisotopes and cellular toxins.
Yes. If attached to a radioisotope like the drugs ibertumumab or tosatumumab, which both target CD20 for lymphoma, the antibody delivers a highly localized, microscopic dose of radiation directly physically to the tumor cell. It spares the surrounding healthy tissue while irradiating the cancer at point-blank range.
And the toxins.
If attached to a chemical toxin, it becomes a molecular smart bomb. And the lecture provides a fantastic, highly detailed example of this, a drug called gemtuzumab ozogamicin.
I love how this drug works. It is the ultimate biological Trojan horse. Let's break down the mechanics of gemtuzumab ozogamicin step by step because it perfectly illustrates everything we've learned about cellular biology today.
This drug is specifically utilized for treating acute myeloid leukemia. Step 1. The targeting phase. The antibody portion of the drug, the gemtuzumab, is engineered to bind specifically to the CD33 protein, which is heavily expressed on the surface of these leukemia cells.
But the gemtuzumab isn't empty. It's carrying a hidden, highly lethal soldier inside.
Yes, attached to the tail of the antibody is the payload, ozogamicin, which is an extraordinarily potent cellular toxin. So the antibody binds to the CD33 receptor on the surface of the leukemia cell.
Step 2, the cell makes a fatal mistake. It opens the gates.
Because of the binding, the leukemia cell initiates endocytosis. It naturally swallows the receptor, pulling the entire complex, the antibody, and the attached toxin inside the cell, trapping it within a digestive vesicle called a lysosome.
The Trojan horse is now inside the city walls.
Step 3. The release. Inside the highly acidic environment of the lysosome, the chemical bond connecting the antibody to the toxin is engineered to break. The ozogamicin is severed from the antibody and released into the internal fluid of the leukemia cell.
In step 4, the hidden soldier attacks the command center.
The free ozogamicin travels directly into the nucleus of the leukemia cell and binds to the DNA. It induces fatal, irreparable, double-strand breaks in the DNA helix. The cell's genome is completely shattered, p53 or not, and the cell undergoes rapid, catastrophic apoptosis.
It leverages the cell's own mechanism of swallowing surface proteins against it, using it to deliver a nuclear bomb directly to the DNA. It's breathtaking how precise that is compared to traditional chemotherapy that just bathes the whole body in poison.
It truly represents the pinnacle of applying our understanding of cellular mechanics to clinical treatment. But the curriculum doesn't stop there. It mentions two final, older, but vital in vivo stimulation therapies we must cover for complete coverage.
Yes, let's briefly touch on BCG and IL-2 therapies. We talked about IL-2 earlier as the cytokine that builds the T-cell army. How is it used clinically?
By intravenously administering massive high doses of IL-2, the goal is to artificially drive an explosive proliferation of the patient's T cells and generate what are called LAK cells, lymphokine-activated killer cells. While it can produce dramatic responses in a small subset of patients, primarily with melanoma or renal cell carcinoma, it induces massive systemic life-threatening inflammation, limiting its broad use.
And DCG. BCG is a tuberculosis vaccine. How on earth does a TB vaccine fight cancer?
It's an incredible example of localized immunotherapy. BCG is utilized specifically for superficial bladder cancer. A solution containing live, attenuated, weakened tuberculosis bacteria is inoculated directly into the patient's bladder through a catheter.
You purposefully infect the bladder with a weakened bacteria.
Exactly. The presence of the bacteria triggers a massive, highly localized inflammatory response from the innate immune system. The bladder lining is suddenly flooded with activated macrophages and neutrophils rushing in to fight the TB infection. In the absolute chaos of this massive, localized immune response, these hyperactivated macrophages also recognize and destroy the superficial bladder cancer cells. The inflammation acts as a localized, nonspecific clear-out of all abnormal tissue.
You create a controlled fire to burn out the weeds. It's brute force, but localized. But if we want to move from brute force to the absolute cutting edge of genetic engineering, we have to talk about the final therapy in the curriculum, CAR T cell therapy.
CAR-T is the closest thing to science fiction we have in modern medicine. CAR-R stands for chimeric antigen receptor. This therapy doesn't just stimulate the immune system, it fundamentally rewrites the genetic code of the patient's own T cells to turn them into unstoppable assassins.
Let's walk through the CAR T process. How do we build this engineered weapon?
First, we extract the patient's own T cells from their blood through a process called leukapheresis. We take these normal baseline T cells into a highly specialized laboratory.
Then comes the genetic engineering.
Yes. Using a deactivated viral vector, we insert a brand new synthetic gene into the DNA of the patient's T cells. This gene codes for the chimeric antigen receptor. It's called chimeric because it is a fusion of different proteins that don't naturally exist together. The outside of the receptor is engineered to bind to the tumor antigen with the incredible precision of an antibody. The inside of the receptor is engineered to deliver a massive, overriding activation signal to the P cell the second it touches the tumor.
It bypasses the need for MHC. It bypasses the two-key failsafe. It's just touch the target, kill the target.
Exactly. We then multiply these newly engineered CAR-T cells by the hundreds of millions in the lab and infuse this massive army of super soldiers back into the patient's bloodstream.
And what are the clinical results for this?
For certain types of liquid tumors, specifically relapsed or refractory B-cell acute lymphoblastic leukemias and certain lymphomas, the results are staggering. In patients who had failed every other available therapy, who had weeks to live, CAR-T cell therapy has demonstrated complete remission rates upwards of 80%.
80% efficacy in refractory terminal patients. That is the power of understanding the immune system. So we have reached the end of our deep dive into Dr. Coitinu's masterclass.
We covered a lot of ground today.
We really did. We have mapped the brutal mutating foundations of carcinogenesis. We have explored the incredible multi-layered complexity of our innate and adaptive immune response. We have uncovered the dark arts of tumor evasion, the smoke screens, the decoys, the hijacked peacekeepers. We've examined the precise molecular footprints we use for diagnosis. And finally, we've witnessed the revolutionary genetically engineered promise of immunotherapy.
When you step back and look at the entire picture, what we are witnessing is the ultimate biological conflict. The human body has developed overlapping, brilliant fail-safe systems, dendritic cells, p53 guardians, the elegant ADCC response of NK cells to protect us from the inevitability of genetic mutation. And the cancer cell, born from our own biology, uses that very same biology against us. It is not just a clump of broken cells, it is a dynamic, adapting, terrifyingly intelligent adversary.
But by understanding exactly how the tumor hides and suppresses, by understanding the specific mechanisms of MIC decoys and TGF-beta and checkpoint receptors, we are no longer fighting blindly with just cut, burn, and poison. We are building dendritic vaccines, Trojan horse antibodies, and genetically engineered CAR-T super soldiers. We are finally learning to turn the tide of the microscopic war happening inside us.
It's an incredible time for medical science.
It is. But before we go, I want to leave you with a final thought to mull over, something that builds on everything we've unpacked today, especially for anyone who has ever known someone fighting this disease. Think about what we learned regarding how advanced tumors actively recruit regulatory T cells.
Right.
Think about how they secrete their own specific cytokines like IL-10 to suppress the environment, and how they build their own dedicated blood supply through angiogenesis. Does this mean a tumor isn't just a random chaotic collection of broken, mutated cells trying to survive?
The fascinating question.
Does it imply that an advanced tumor crosses a threshold where it's actually acting more like a rogue, highly organized parasitic organ that actively engineers its own specialized survival ecosystem within your body? And if tumors are acting like rogue, intelligent organs rather than just chaotic cells, what does that mean for the next 20 years of immunotherapy? How do we treat a disease that doesn't just hide, but actively governs the space around it? Keep digging, keep questioning, and we'll see you on the next deep dive.